Hi, I am Nina. I am an AI engineer at Research and Development Division in Intexel. Also, I'm a master's student at Arizona State University, majoring in computer science. And today I am presenting multi-center, multi-vendor, and multi-disease cardiac image segmentation using scale-independent multi-gate UNET. So, cardiovascular disease is a term used with the diseases that affect either the heart or blood vessels. And actually, it is the number one cause of death globally. And cardiovascular diseases are common in high income, low income, and middle income countries. However, in low and middle income countries, people do not have the benefit of integrated primary healthcare programs to diagnose these diseases. Also, one more issue in these countries that the number of patients or the number of doctors to the number of patients is quite low, making it harder for a patient to get his scan analyzed and diagnosed. And a large number of approaches have been proposed to tackle this problem, and they broadly can be classified into two categories: the classical approaches and the deep learning based approaches. One of the classical approaches that's early discussed or early proposed the multi-level thresholding. And the idea is it minimizes an energy function given a grayscale image with multiple classes in it. It tries to maximize the intra-class variability or the variability between classes. However, the issue with this approach is when the model size or the size of object of interest compared to the background area is small, it fails. And this is actually present in our case, since in MRI images, cardiac MRI images, the area of the heart compared to the background area is quite insignificant. Also, some other approaches like graph cuts, deformable models, and active shape contours have been proposed. However, the issue with these approaches is that they lack the ability to generalize well with unseen data outside the training set. For the deep learning based approaches, there have been proposed many models. However, one of the most successful models that are based on encoding and decoding architectures. UNET is one of these models, and it is a very successful model for medical image segmentation. However, in multiple studies, it was noted that when segmenting the apical slices, the model performance degrades a lot compared to basal and mid. So it lacks the ability to overcome size variability between slices. So in essence, we have multiple challenges that we want to address, that we want a model to be accurate enough to be used in real-life applications. We want it to be fast, also to be robust to size variability present in cardiac MRI images. Also, we want the model to be aware of context. Since now we are trying to segment images coming from multiple vendors and multiple centers, we would like the model to be able to focus more on the big picture, not on the fine details of each vendor or each center. So it's not a vendor or center specific. We want it to be more of aware of the context of the whole image, so it can generalize well when tested on other vendors. So we propose a pipeline consisting of two steps. The first one is heart localization. The motivation of heart localization is that the heart area compared to the background area is quite small. So it is more efficient if we can cut or crop this area of interest and segment this area alone, focus on this part of the image instead of wasting time with a big image mostly unrelated to us. We do not care about the background here. So we need a lightweight model since it's just a pre-processing step for the later step, which is segmentation. And we want it to be accurate enough to be able to localize the heart well within the image. For this reason, we chose to use LevelNet. LevelNet was proposed by Dina and her colleagues. And the purpose of LevelNet was to localize only the left ventricle of the heart in MRI images. However, we here extend this method to get the center of the whole heart, including the left ventricle and also the right ventricle. So basically, the input to this network is the MRI image, and the output is usually segmentation of the whole heart, LV and RV combined, but as one object. It does not differentiate between classes here. It just uses either it's a heart or a background label. And from this segmentation, we can actually, from the geometry of the shape, we can detect the heart location. Then comes the heart segmentation. Here we propose an enhancement to the UNET architecture to make it more robust to changes in size and also to make it more context aware of the images. Of course, now the input to the model would be the cropped version of the previous step. And the improvement that we added to the UNET architecture is the multi-gate block. The multi-gate block consists of two smaller blocks. The first one is the dilated reception block, and it basically gives the network multiple scales of the same multiple scales of the features in order to make it more robust to changes in size. Also, the average pooling, which serves as a context aggregator in the network, as will be discussed in the following slides. Well, kernel size when designing a deep convolutional network is very important, since the small kernel size tends to identify local features. However, the large kernel size tends to focus on more global features. However, increasing the kernel size will dramatically increase the number of parameters in the network, making it slower. Dilated convolution is a special type of convolution where we add like holes between the kernel values. For example, here on the left we have a 3x3 kernel with dilation rate of 1. On the right we have a 3x3 kernel with dilation rate of 2. And the advantage of dilated convolution, it actually can increase the field of view of the network without actually increasing the number of parameters. The inception architecture were actually introduced to solve the kernel size problem. It introduced multiple parallel kernels to the input, and these inputs are going to be concatenated together to fuse them somehow to get a better representation when the object of interest size changes within the image. So here we combine the inception architecture with the dilated convolution into a dilated inception block, where the input to this block gets passed to 4 parallel convolution, varying in size, in kernel size, and in dilation rate. And these the out features of these kernels are going to be concatenated, then combined by using 1-by-1 convolution to reduce the total number of features and keep the model small and fast. The results of our models of our model for our pipeline suggests that there is an ability to generalize over multiple vendors. For example, in this figure, we show the dice for LV, RV, and myocardium, and along the x-axis or horizontal axis, we plotted for each vendor. So it seems that from the box plots that the dice score is almost or very consistent across different vendors. It does not swing between one vendor and another, meaning that the model able to generalize despite it was actually trained on vendor A and B, then it was tested on C and D. Also, there is another table for dice scores per center and vendor. It also seems that the model is able to do consistently among centers. However, in center 6, it's a bit lower than the others. However, in overall, the scores are very close to each other. So in this paper, we introduced an enhancement to the native UNET where we made it more robust to changes in size and also made it more context aware so it can generalize better for other vendors. The localization network we used actually led to an enhancement of the results by 2.5% for the dice scores for the LV, RV, and myocardium, respectively. So it was a useful step. The overall pipeline is quite fast. It's taking 0.002 second image when tested on an NVIDIA GPU 1080 Titan X. The model also is robust and able to generalize to other vendors and centers that were not actually included in the training data. And thank you.